Okay, hi everybody. So today we're going to continue 4.7. This is part 2, and we're going to be looking at the antiderivatives of functions. And we're just going to do a couple of examples, and then we'll do some applications. And there's most likely going to be a part 3 because I don't want to make this video too long. So let's do a couple of examples. Okay, so I want to find the most general antiderivative of a, let's do f of x is equal to cosine x. So remember that when we were discussing antiderivatives in part 1, I said an antiderivative is really just the opposite of a derivative. So if you have an antiderivative and you take the derivative of the antiderivative, you should get back the original function. And when we denote antiderivatives, we denote it with a capital F of x for this section. And so what you want to do is think about this. If you're looking for the antiderivative of cosine x, you have to think about what derivative gives you cosine x. So recall that the derivative with respect to x of sine x gives you cosine x. So this tells you that this one here is the antiderivative of cosine x. So this means that capital F of x is equal to sine x. But we're not done here. Remember that we can't forget the plus c is the antiderivative. Okay, and then I'll write a list of a couple just common antiderivatives that are going to be useful for you to know. So this right here is the antiderivative to f of x is equal to cosine x. Okay, now let's do b. So for b, we have f of x is equal to e to the x. And this one's super easy because remember, you want your antiderivative to give you back the original function, but recall that the derivative of e to the x by itself, with no constants in front, is equal to just e to the x. And so for this part so far, I'm not going to include any constants here just yet. I don't want to do that to you right now just because right now you're simply just learning antiderivatives. Just like if I was teaching you derivatives, right, you don't want me to start with the most complicated thing like chain rule. So I know that you're probably thinking, hey, what about if you had a different constant there? How would that work? And it'll work a little bit differently, and we'll go over that in a later section because we're going to do something called like a backwards chain rule, which is a little bit complicated, so I don't want you to worry about that now. So everything in this section, you won't have to do any backwards chain rule stuff. So just keep that in mind. Okay, so now let's do one more example. Let's do C. And so these are very common antiderivatives that you should know, but I just want to get you thinking about them and saying, okay, what's the derivative? What function gives me that derivative? So we have f of x is equal to 1 over x. And so now we have to think about something that gives us the derivative, that when I take the derivative, I get 1 over x. So go ahead and think about that for a second. But recall that the derivative, and hopefully this is what you thought of of the ln of x, but here we have to specify absolute value of x is equal to 1 over x. Because what we know of this function here, f of x, is that here x cannot equal 0 at all for any reason, because it's undefined. But if we're looking at this function by itself, we can't exclude the negative values, right? Because 1 over x could be negative, sure, yeah, it can. But we know that when we have the ln function, we don't have any negative values. So when we have to specify that we're doing the absolute value here, because our ln function can't take on negative values, but 1 over x can take on negative values. So you have to specify those absolute value bars. They're super important for you to specify. Okay, so that's the antiderivative of 1 over x, but sometimes people, and this will make sense, the general antiderivative, we'll write it as capital F of x is equal to ln of absolute value of x plus our c constant, because remember that an antiderivative can vary by a constant, and this is for x not equaling 0. So we still have to include that in our domain. You might also see the book write this in a different way. And you can also write it this way, is you can write, remember that we learned that you can write the ln function as a piecewise function. So let's go ahead and try that. We can write ln of x plus some constant if x is greater than 0. So strictly greater than 0, we don't need the absolute value bars anymore. But if x is less than 0, we have to do something to the ln function so that it is no longer negative. So we'll put a negative x. So that way, if we ever plug in a negative value into here, it'll cancel out with that negative, and then we'll just be left with the positive. And we can't forget this plus c. Now, here, I'm actually going to do something a little bit different. I'm going to include subscripts here as C1 or C2, or you could even do C0 and C1, but I'm going to keep it as C1 and C2. And so, because the reason that we're doing that is because this really is just one constant. And here we want to specify that, yeah, they could be the same constant, but they could also be different. So just keep that in mind, and we need to write that for that function. Okay. And now what we want to do is, I want to go over some general antiderivative formulas. And again, this is going to feel very similar to when we were starting to learn derivatives, where I just gave you a bunch of functions and I said, here's a derivative. Well, now we're going to take a bunch of functions and now we're going to specify the antiderivative. And this is just some general antiderivative formulas. Not all of them. There's a lot of them, actually. But, you know, we'll go through them step by step and we'll just take it easy. And so if you remember at the beginning of the semester, I gave you a sheet with all the derivatives, and all the antiderivatives are on there too. You just didn't know it then, but they're on there. So if you still have that sheet handy, and I believe it's also on titanium, then everything should be on there. So let's just talk about some of them, and more will come up as we keep talking about antiderivatives, so don't worry too much. Okay. And then there's some in your textbook, I believe in page 249, because I'm not going to go over all of them. Some of them you don't really, I didn't want to go over too much. I just wanted to go over the more complicated ones for now. Okay, so the first one is if we have an x to the n with obviously x cannot equal -1, we're going to do that backwards kind of power rule. that we talked about at the beginning of the section. So remember that I said that if we wanted to go backwards over here, then we would increase the exponent by 1 and then divide by the new exponent. So that's exactly what the backwards power rule will do for antiderivatives. So you're going to increase your exponent by 1. So now you're doing the opposite of when you did a derivative. When you did a derivative, you pulled that power up to the front and then subtracted by 1. And now we're compensating for that since we want the antiderivative by adding 1. And now we're going to also divide by n plus 1. So remember that when you have the antiderivative, you always divide by that power. They're the same. And since these are what are called definite integrals or general antiderivatives, we're going to need to include that plus c. We always need to include that plus c. The next one is the one we just learned about, which is 1 over x. The antiderivative is the ln of the absolute value of x plus c. And we also did e to the x. And so the antiderivative of that is e to the x plus c. And now I want to do the antiderivative of cosine x. I believe in the last, oh, we did do that one too. So the antiderivative of cosine x is sine x plus c. Move this down a little bit more. And then let's do sine x. Okay. So the reason, if you recall in the last example, that the antiderivative of cosine x is because if we take the derivative of sine x, we actually get cosine x. Yes. But now we have the function sine x, and we need to think what derivative gives us cosine x. Well, that's actually going to be negative. Sorry. We have the function sine x, and we want to think about which function, if we take the derivative, will give us sine x. And we know that derivative is cosine x, but when you take the derivative of cosine x, you get negative sine x. So we need to throw on this negative sign in front of it here, so that when we take the derivative, we get a positive sine x. So it's going to be cosine x plus c. Derivative of cosine is negative sign, but the derivative of negative cosine is negative sign, which will give us that positive sign. Okay, now let's do a couple more. Let's do secant squared x. And so for a lot of these, just think, oh, if I take a derivative of something, what's going to give me secant squared x? And that's just your tangent x plus c. And now we also want to do, let's do some arc functions or some inverse trig functions. So 1 minus x squared. Does anybody remember this derivative? Hopefully you're thinking in your head that it's, oh, that's my arc sine. So this is sine inverse of x plus c. And let's do one more arctangent and then we'll be done for now. Like I said, there's a ton more, but we'll just start off with a couple of them till we get the hang of it. Because thinking about derivatives backwards is a new way of thinking. And it's not very hard, but it takes time. So just keep that in mind. And please email me if you have any questions, or come into our Zoom meetings if you can't do the homework or this was confusing. Okay, so here we have our 1 over 1 plus x squared. And I was talking so much that I went ahead and wrote it, but that's okay. So remember that the that the derivative of arctangent gives us this. So that's where that's coming from. Okay, so now let's do a big derivative. So what I want to do now is, before when we did a couple of these, they just included one function. Now what I actually want to do is, let's just do a big example of a random function that includes all of these, or not all of these, but some of them. Let's do an example. Let's do find all functions h That does not look like an H. H such that H prime of X is equal to 7X to the 2/5. So you guys can see that. Let me get a little bit more zoomed in. Plus 8x to the negative 4/5 plus 3 sine of x. Okay, so here they phrase this a little bit differently, but it's really the same thing as finding the antiderivative, because what they gave us was the derivative, and they want to know the original, they gave us the derivative and they want to know the original function, just h of x. So they want to know what's a function that we can get here that'll give us this derivative over here. So we're really just, they're giving you a fancy way of saying, hey, find that antiderivative. So there's different ways that it'll be phrased. Get used to all of them, and then I'll do an example of the different ways that they can phrase it just so that you're comfortable with it as well. Okay, so we want to find that antiderivative. So what we want to do is we want to find, so you have this in your notes, the antiderivative of, and then what we're going to do here is just write the original function that they have here, 7x to the 2/5 plus 8x to the negative 4/5 plus 3 sine of x. Okay, so that means that we are looking for h of x, so that when we take the derivative of h of x, we get this over here. So hopefully we're all understanding that. And again, all of this takes a little bit of time, so I'm actually going to go step by step for this one because I included some fractions. I thought that would be fun. Okay, so here we have an x to some power, right? I don't really care about the constant, just like when you have derivatives, you don't really care about the constant either too much. So what we're going to do, I mean, the constant is there, but it's not going to affect how we're going to take that antiderivative or the derivative for this problem. So here I have x to some power. So let's go back for a second here, and let's look at where we have x to some power. Oh, I found it right here. So what we're going to do for this one is we're going to take our x, we're going to increase it, our exponent, by 1, and then we're going to divide by 1 as well. So let me show you what we're going to do here. So we're going to get 7, we're going to get x, and then we're going to have that 2/5. I'm going to leave that by itself. But now we're going to add 1 to it. And adding 1 is the same thing as adding 5/5. I just like to get the denominators the same while I'm at it. And then we're going to divide by 2/5 plus 5/5. Again, I'm being extra. I'm showing you all the steps. I think it's really important that you actually write all the steps while you're learning this. Once you're comfortable with this, you don't have to do this. And then now let's move on to the next one. Again, here we have x to some power. Sure, that power is negative, but it's still a power. And that power, as long as that power doesn't equal 1, we're okay. I mean, -1, we're okay. And so now what we're going to do is we're going to do the same thing as we did in this last one. We have our -4/5, and then we're going to add 1. Adding 1 is the same thing as adding 5/5. And so we're also going to divide -4/5 plus 5/5. And now we're going to take the derivative of sine x, the antiderivative of sine x. And if you recall the antiderivative of sine x, let's go ahead and look. It's good practice to just look, right? So we're looking for the antiderivative of sine x. We have the function sine x, and we want its antiderivative. Oh, that's cosine, negative cosine x. So it's going to be 3 times our negative cosine x. Doing it in a different color so that you see that we where we applied those antiderivative rules exactly. And then don't forget the plus c. Please don't forget that plus c. Okay. Now let's just simplify. So now what we are going to do, let's write 7x to the, we add the exponents together, we'll get 7 over 5. And then in the denominator, we'll also get 7 over 5 plus 8, x to the 1 over 5, easy peasy. And then denominator 1 over 5. And then let me just rewrite this so it doesn't look all crazy. So negative 3 cosine x plus c. Beautiful. And now I don't want to see a fraction over a fraction because that's ugly. So I'm going to go ahead and flip this over so that it looks nicer. When I flip it over, the 7 will cancel out with the 7. And so we'll get 5x to the 7 over 5. Here we have 8 divided by 1 over 5. We'll multiply them together and we'll just get plus 40 x to the 1 over 5 minus 3 cosine x plus c. So that is our antiderivative. So this is our capital H of x. And again, you can always check this by taking the derivative, by doing h prime of x. So I'm not going to fully do it, but let me just walk you through it a little bit. Take the antiderivative of this, bring this 7 over 5 over to the front. Yeah, the 5s will cancel out. I'll get 7 minus 1. That's definitely this term here. So always check this, and then hopefully you'll get your antiderivative up here. Okay, super important, especially when you're first learning it. And even like just moving forward, it's just good habits to check it until you're like 100% comfortable. Okay, so now what we're going to do is we're going to do some applications. So there's 2 reasons we take antiderivatives. But the one that makes more sense right now is for the applications of it. I mean, the other one is also an application, but this application you've seen before. The next application we're going to talk about is area under the curve, but that's not till the next section, and it's a kind of slightly different idea, so I don't want to get into it in this section. So we'll just strictly go to the applications that we did with our derivatives as well. So remember that S of t is equal to our position function. Or you could have also called it R of t, whatever, it doesn't matter. And remember that if we take the derivative of S of t, right, we end up with our v of t, which is our velocity function. This is all stuff we've done before. And now if I take the derivative again of s prime of t to get s double prime of t, we get our acceleration function. So we're just recalling all of this, which was our acceleration. Okay. When we go ahead and take the derivative, so over here downwards, we have our derivatives. But now we're talking about antiderivatives. So if we go down, we take the derivative of s of t. We get velocity. We take the derivative of velocity, we get acceleration. But now, what if they give you acceleration? How do you get up here? You do it by taking antiderivatives. So if we actually go ahead and go backwards from the bottom up, starting from here, or from here, it doesn't matter. If you just move upwards and take antiderivatives, you'll actually be able to get other functions as well. So for example, if there's a problem where they give you, hey, here's a velocity, please let me know the position. Now you know how. You take the antiderivative. Or if you are given the position, but you want to know acceleration, you know that you have to take derivatives downwards. But if you're given acceleration and you need to know the position, then you have to take an antiderivative of this to get to velocity, and then the antiderivative of this to get position. So let's do an example so that you see what I'm talking about. But hopefully this little diagram makes a lot of sense, or makes some sense, hopefully. Okay. I like this application because it's not something really new. You already knew all of this. You knew the position function. You knew that the velocity was the derivative of the position function and the acceleration was the derivative of the velocity function. And now when you're doing antiderivatives, you just have to kind of flip everything. So you're not learning anything new, you're just thinking about it in a different way. So I think it's cool. So let's do some examples. We'll do 2 examples of this. Just so you get the hang of it. So let's say a particle is moving with the given information. We're going to do 2 examples of this. Oops. I want you to find the position of that particle. Okay, so the first one we're going to do is there's going to be 2, remember, is going to be v of t is equal to 2t minus 1 over 1 plus t squared. Now I'm going to show you something a little bit different, and then we're going to say that the position, the initial position at time 0 is equal to 1. Okay, so they gave us our velocity function. We want to know the position function. So if we look at our diagram, we're right here and we want to be right here. So what we need to do is we need to take one antiderivative upwards to this part here. So we just need to take the antiderivative of this, because remember that the derivative of the position, oh my goodness, what's going on with my writing? The derivative of the position is going to give us the velocity function, so we need to take that antiderivative. So when we take that antiderivative, okay, go ahead and pause the video and see if you can do it yourself. It's a good habit, but I'll keep doing it here. So if I take that antiderivative, why did I do that in black? I mean red. If I take the antiderivative, I'm going to get 2t. I need to increase my exponent by 1. I have a 1 here, plus a 1 here. So I'm going to do 1 plus 1 at the bottom, which is this 2. And then what do I do with this? I don't know. Hopefully, maybe when you pause the video and try it yourself, you're like, I don't know what to do. Let's look. Let's look. Does any of this look familiar over here? Oh, I see it. It's my arctan. So not here to trick you, just showing you. So for that piece that we just looked at over here, it's going to actually be arctan. So the antiderivative of 1 plus 1 over t squared is arctan. So remember, like I said, all of this just takes practice. It's nothing too crazy. You'll get used to it. And we're going to do inverse tan of t. And then we can't forget plus c, because I'll cry. You don't want me to cry. Okay, now let's simplify this a little bit. So then we're going to get s of t is equal to, so I'm just going to do this all in one haul. 2 over 2, that's just 1. So then we're going to get t squared minus tan inverse of t plus c. And then you could always check this by saying, okay, if I take the derivative of my position function, am I gonna get this over here? And the answer is yes. So, but now what do I do about this? because the problem here is they wanted to find the position function, right? But right here, I actually don't know the position if I don't know this C at all. I don't know it. So how am I supposed to give you the position function if I don't know C? But good news is they gave us this extra condition right here. So let's see what that does. So we're just going to use it. Let's see what happens. So they told us that S of 0 is equal to 1. S of 0 equals to 1. Okay, so since S of 0 equals 1, if I do S of 0, that's going to be 0 squared minus inverse tangent of 0 plus C. But they told us that S of 0 equals 1, so actually I can go ahead and replace this for my 1, because that equals 1. And now this is going to go away. Arctan of 0 is just 0, and then we are just left with that plus C here. So 1 is equal to C. So that tells us that S of t is equal to t squared minus tangent inverse of t plus 1. And that's our answer. So if they give you extra conditions, you can use that to find that unknown constant value. So that's something new, and you didn't know that before, but now you do. So let's do one more. Again, we're going to be finding the position function, but I actually want you to try it. I want you to try it. I'll do it myself as well, but I want you to try it on your own first. Please just don't not pause the video. I want you to actually try it. So we're going to find the position of A of t is equal to sine t plus 3 cosine t. Now I'm going to give you two conditions. I'm going to give you that the position at time equals 0 is equal to 0, and that my velocity at time 0 is equal to 2. So go ahead, pause that video, and figure out how am I going to get to my position function from my acceleration function. And it might be a good time to kind of look at your diagram here and go, how do I get from here to here? Okay, so let's do that. So hopefully you realize that you're going to have to take the antiderivative of A of t. When you take the antiderivative of A of t, you get V of t. But then that's still not S of t, so you're going to have to take the antiderivative of V of t to get you S of t. So let's go ahead and do that. So I need to take my antiderivative of S of A of t because I know that the derivative, so since my derivative with respect to t of V of t gives me A of t, I know that I have to take that antiderivative. Also, you don't have to write this each time. I'm just, for your notes, you could have just looked at the diagram as well. So that means that I need to find V of t, and I'm going to do that by taking the antiderivative of this. Okay, so let's take that antiderivative. So my antiderivative of sine is negative cosine, and if you don't remember that, it's a good idea to look back at it's okay if you don't yet. I know it's confusing. I know that when I first learned antiderivatives myself, I would always go, oh my god, which one's negative, which one's positive, because I was so used to derivatives. So don't feel bad that you're getting them confused. It's perfectly normal. Okay, so my antiderivative of sine of t is cosine t. And now my antiderivative of cosine t is positive sine t. So I'm going to do 3 times my sine of t. And I'm just doing this in a different color so that you see where I took the derivative, and we need that plus c value. Okay, now what you want to do here is you don't just want to take the derivative again. yet. I mean the antiderivative again yet, because we don't know that plus c, and eventually I want to get the position function with everything I know. So we're actually going to use this condition here and substitute this in here and say okay, so that we can find that c value. So we're going to do v of 0 equals 2. So what we're going to do now is we're going to say that 2, because that's v of 0, is equal to negative cosine of 0 plus 3 sine of 0 plus c. Okay, so now what we want to do from here is we want to just solve for c. So cosine of 0 is just 1. And then sine of 0 is just 0. And so then if we solve for c, right, we get 2 equals negative 1 plus c. We get c is equal to 3. So that means our velocity function is negative cosine of t plus 3 sine of t plus 3. Perfect. But we're not done. We wanted the position function. And so that means we have to take another antiderivative of this to get s of t. So s of t is going to be the antiderivative of this. The antiderivative of cosine is sine, but we have a negative in front. So we'll do negative sine of t. And then plus 3. And remember that the antiderivative of sine is negative cosine. And then if we take the antiderivative of 3, I didn't really go over this, but we have a constant here, right? So now we have to think about, okay, what if we take the derivative of something with respect to t, what's going to give us 3? And that's if we have plus 3t. Because if I take the derivative of 3t, if I take the derivative of 3t, I get just 3, my constant. And then we can't forget the plus c. Oh no. Okay, so now from here, we want to use, let me rewrite this so it's all nice. So then we get negative sine t minus 3 cosine t plus 3t plus c. And now we want to use what we got here, which was s of 0 is equal to 0. So we'll use s of 0 equals 0 to get our value for c. So what we're going to do now is we're going to do 0 is equal to negative sine of 0 minus 3 cosine of 0 plus 3 times 0. I'm just doing all these extra steps so that you can see it. And then we know that sine of 0 is just 0. Cosine of 0 is 1. This is just going to go away because it's 0. And so we get 0 is equal to negative 3. And so, and then plus c. Because this went away. Sorry, you can't see, but I'm pointing at it. Because this went away, and this went away, and then we had the negative 3 in the front. And so that tells us that c is equal to 3. Again. So then what we're going to do from here is we're going to just substitute that back into our position function and say that our position function s of t is equal to negative sine of t minus 3 cosine of t plus 3t plus 3. And that's our position function. So you can use these values, and so we call these initial values, so that we can find our constant c. Okay, And so after this, what we're going to do is we're going to go over a few more examples just because the book phrases it in different ways, but we're really just going to be doing the same thing over and over again. I might go over one more example probably in the next video because this video is kind of long. So see you in the next one.